lecture. And then Lauren, you can start sharing your screen. And then we have the CGU-HS AGM Friday evening, afternoon, depending on where you're from. So please try to attend that. So our first speaker is Lauren, talking about drivers of hydrological response for distinct wetland complexes in a high latitude alpine watershed.
Hi everyone, my name is Lauren Burke. I am a master's student with Sean Carey at McMaster University. And as he said, I'm going to be talking about drivers of hydrological response for distinct wetland complexes in a high latitude alpine watershed. So wetlands are abundant in northern areas, and they can play a critical role in the hydrological functioning of the landscape. They store large amounts of water, they filter sediments, and they're critical for runoff regulation. So where these wetlands are located in the landscape will likely play an important role in how alpine wetlands respond to precipitation and what this means for storage and release. So in discontinuous permafrost regions, water storage is important as these regions change with climate change. So the main objectives of this study were to determine how the hydrological function of two distinct alpine wetlands, and then to evaluate these characteristics and drivers of water table dynamics to compare the responses of these two environments. So this study took place in Wolf Creek Research Basin, which is located in the traditional territories of the Kwanlin Dun, the Tonquachin, and the Karkrosh-Tagish First Nations, which is located about 15 kilometers south of Whitehorse, Yukon Territory. So wetlands have been well documented in this area, but relatively little is known about them. There are often two distinct types in this area. So there are wetlands that are located in the valley bottom, and then those that are perched in the landscape. So a wetland of each type was chosen for this study, and shallow water table wells were installed at each sites, and stable water isotopes were taken weekly. So these stable water isotopes were taken at the margins of the valley bottom wetland at 3 different ponded areas of the perched wetland, as well as an outlet location. So these are our wetland sites. So this site here on the left is the perched wetland. So it's isolated in the landscape. There's no channel inflow or outflow. And as you can see, there's 3 distinct ponded areas. So they have relatively small drainage areas as expected. So their drainage areas are 0.036 kilometers squared for the first one, 0.747 kilometers squared for the second one, and 0.216 kilometers squared for the third one. So these 2 ponds were hydrologically connected very early in the season, with areas that had grassy areas that with water ponded on the surface at the beginning of the season until the water table drained. And so this one here is the valley bottom wetland. So this wetland consisted of multiple wetland complexes, with this 1 kilometer portion being our main area of study. So it consisted of 2 main pond areas, and then an area in the middle that was grassy and had water ponded on the surface all year round. We also studied some areas here in the south that aren't pictured on this map. They similarly were grassier areas with water ponded on the surface throughout the entire season. So this area also consisted of a beaver structures. So in the northern area, we saw a large beaver influence, which impacted the hydrology of the area. It created an area with braided creeks until they eventually merged into an outlet. So it had no known channel inflow, but it did have an established channel outflow. And the area of this wetland was about 7 kilometers squared. So the water table is important to understand how these different wetland types in Wolf Creek will respond to precipitation. So we measured the water table at each one of these sites at 15-minute intervals throughout the season and compared it to precipitation data that was collected near this wetland. So as you can see, they don't have a lot of responses here in this valley bottom wetland. So these 3 are the ponded sites. They show very little change throughout the season, and all of these margin water table wells are very similar. They don't show a lot of change. And so during this largest rain event, like this largest daily rain event in August, there's barely any response. The magnitudes are all different. The pattern is different. The timings are different. And the largest response was 6 centimeters. And in total, their responses were between 1.5 to 6 centimeters through this valley bottom wetland. This perched wetland told quite a different story. So same thing, these are the water levels we collected at each site with these 3 ponds. This first pond actually ended up going dry before August, so we only analyzed these second ponds. So As you can see, the timings and the magnitudes are very similar in the perched wetlands. They all have very comparable magnitudes. They have the same time that they respond. And during this same daily rain event, the largest responses were much higher. So the responses were between 20 to 40 centimeters compared to the 1.5 to 6 centimeters in the valley bottom wetland. So this is likely just showing that the connection in the landscape in the valley bottom wetlands created a slower and less notable response compared to the perched wetland. So next we were looking at how the flow changes within Wolf Creek. So how does the discharge of the valley bottom wetland vary from other areas in the basin? So the perched wetland had no channel outflow, so we just did this for the valley bottom wetland. And since wetland areas are assumed to be important water storage in Wolf Creek, it was important to determine how this would impact the area. So to do this, we used one other stream within Wolf Creek. We used the Granger stream, which is this area here in blue. We chose this because it's a very similar drainage area to the wetland, with a drainage area of about 7.3 kilometers squared versus the 7 kilometers squared of the valley bottom wetland. The valley bottom wetland outlet was located at a little bit of a distance from the main study area. This area in between had other wetland complexes that we couldn't access. And this outlet does have one more stream that does flow into this outlet, but other than that, it's just the wetland waters. So you can see that these trends are relatively similar between Granger and the valley bottom wetland, but the Granger Creek showed higher responses to rain events with higher peaks compared to the valley bottom. So in the early season, the valley bottom wetland was higher than Granger Creek, likely just due to the large impacts of the snowmelt in this wetland. And then later into the season, as the weather started to cool, Granger saw a large recession, which wasn't seen in the valley bottom wetland. So this is pointing likely to the wetland stability throughout the season, with precipitation and temperature having relatively little effect on the actual discharge and flow throughout the season. Next, we looked at the stable water isotopes at these wetlands. So we took these weekly at 3 of the ponds and at 3 margin sites within the valley bottom wetland, and then at the outlet at the valley bottom wetland. So we created a local meteoric water line from precipitation data dating back multiple years. And then we used this to determine how these waters are changing within this watershed. So we analyzed the distribution, and you can see that these perched wetlands have a much larger distribution in both deuterium and oxygen. They change largely throughout the season, whereas the valley bottom wetlands, they remain clumped together. They're quite small and they don't change a lot. There are some small differences within the valley bottom wetlands. Often as it was flowing towards the outlet, they'd become less negative, and then back towards the outlet, they become depleted again, which is likely just due to the mixing on the stream that was also supplying this outlet. So then we calculated the deviation from the local meteoric water line using line condition excess. And so as expected with these large distributions, the LC excess at the valley bottom wetland was much smaller, with an average value of negative 3.6 compared to negative 14.6 from the perched wetlands. From this, we tried to determine how the season impacted these isotopic responses at each site. So as you can see in June, the only site that we could access was the perched wetlands, just due to the large snowfall. So we couldn't quite access the valley bottom wetlands yet. So in June, these areas, they're clumped closer to the local meteoric line than any other time in the season. They're closer together in general. So it's showing that there's likely less evaporation early in the season. Their dominant source is snowmelt at this time. And then later into the season, these perched wetlands flow up a local evaporation line. And by September and late into August, the first perched pond was already dry. So there are no points from those. And then you can see that these valley bottom wetlands, they remain clumped together. They're all very close together, and they remain very close to the local meteoric water line. So the valley bottom wetlands, since they didn't show a significant trend in the seasons, it points to this constant discharge of water from the slopes in these areas. So in summary, we were trying to figure out and determine how these wetlands compare to each other and how they're changing throughout the growing season, which will likely impact their role in the basin. So we created these conceptual models to indicate the different fluxes and drivers in the wetlands and how that's impacting the water table dynamics. So in the size of these arrows, they indicate the approximate size of the influence of these factors. So the perched wetlands did change seasonally, but essentially had two main responses. Early in the season, in the spring, the snowmelt was the main contributing source. Water levels were high in the spring and early summer, which you can see here in this diagram. And so we're assuming during the cooler season, evaporation was relatively small and there was no visible outflow, so they just remained a closed basin. The second portion of the perched wetland was the late summer. So at this point, there's no snowmelt contributing to this area, and they rely heavily on precipitation. So these areas rely on the absolute volume of precipitation events to sustain them and to keep their ponded areas with water in them. So you can see that the evaporation was much higher. We saw that both in the isotope values as well as in the water table decline. So evaporation became the driving factor to water loss in these wetlands, and the water needed to be sustained in this pond was from precipitation. But even during high rain events in August, they didn't impact the water level as much as we had expected. And the valley bottom wetland had multiple different portions during the growing season. In the spring and early summer, snowmelt was the dominant source, which was coming from adjacent hill slopes. Discharge at this time was the highest due to inflow of the snowmelt, and then it decreased until reaching a steady state in August. In this time, seasonal frost was found in these areas, which lasted until early summer. So in the early summer, there was a little bit of snowmelt left, which were seen at the tops of the hill slopes and mountains, but there was very little vertical gradient present in the wetland piezometers, with a small amount pointing to wetland flowing into the groundwater outputs through the season. So finally, in the late summer, there's no snowmelt contributing to these wetlands. They rely solely on precipitation and overland flow. And in mid-August, the vertical gradient actually reversed in this first pond, pointing to a small amount of groundwater inputs. In the fall, in late August and early September, water levels stabilized and the first ponded area actually began to increase. Evaporation and ET declined with senescence during this time. And late into the fall, small amounts of snowmelt became inputs along with the rain. So isotopic compositions of wetland waters remained similar throughout the entire season, varying only slightly with precipitation, indicating that even during high temperatures, water were sustained by surrounding hill slopes and transited the wetland relatively quickly. So in conclusion, we determined that the landscape position of wetlands did impact their role in Wolf Creek. The valley bottom wetland was supplied by water from the surrounding slopes and required less rain to sustain these areas through the season, while the perched wetland experienced greater responses to rain events and was subject to greater water table decline when there was no snowmelt or large rain events to sustain these waters. So as precipitation regimes change and areas of permafrost change, these areas that were once connected may become disconnected, which can change wetland storage and waters in these alpine regions. So I thank you for listening, and I'd like to thank everyone that contributed to this project and all of our funding sources. So thank you.
That was great, Lauren. Did you do the pictures, the side profiles? Did you make those yourself?
I did make those myself.
That is very talented. Those are excellent.
Thank you.
Do we have any questions for Lauren? Feel free to put them in the chat, or you can kind of ask them out loud. We've got about a minute before we'll get Evan to start.
I guess I'll ask a question, if I may.
Yeah, Andrew.
Just a simple one. Why do you say these are perched wetlands? What's the sort of evidence?
Oh yeah, so they were like located very high in the landscape, so they were kind of perched in these areas that flowed downwards. There was nothing coming into them from the sides of the hill slopes. They were just isolated in the landscape and were just perched locally, sort of. So we just kind of use that term as areas that just kind of like remained perched on the tops of hills, on the tops of valleys, and just didn't have any inflow or outflow.
Okay, because when in groundwater, when we say perched, we mean it's somehow isolated from the groundwater system, right? Like a perched aquifer. Is it the same sort of meaning, or is it different?
in a lot of ways, they were kind of isolated from the groundwater. They had no groundwater inflow, and they kind of just like were their own closed basin. So sort of, I guess, but I didn't really think that one through, I guess.
Okay. So I think what you're saying is a closed basin is what you mean. Okay.
Yeah, I think so.
Great. Thank you.
Okay, excellent. We will get Evan up and running so we can stay on time. So our next speaker is Evan, talking about exploring variability in thermokarst lake water balances in the Nuvik-Tuktoyaktuk region using water-tope isotope tracers. Take it away, Evan.
Thank you. So yeah, I'll be talking about part of my PhD, the title which you just heard. And we can get right into it here. We'll give a bit of background about the study region. We're looking at the tundra uplands that are east of the Mackenzie Delta in the Northwest Territories. So right up in the northwest corner of the Northwest Territories, where there's a Nuviala wetlands and also Quitchin settlement region. So this region is covered by continuous permafrost across the whole landscape, and there's some permafrost beneath some of the lakes, but if the lakes are large enough and deep enough, there's typically no permafrost beneath them. In Inuvik, it's about an average of -8 air temperature and only about 250 millimeters of precipitation a year, while in Tuktoyaktuk, it's a bit colder and they get only about 175 millimeters of precipitation a year. So quite a dry region overall compared to the rest of Canada. In terms of vegetation, it's the tundra, so we don't have really, there's some trees, but it's mostly shrubs, grasses, lichens, and mosses covering the landscape. And the vegetation tends to be a bit thicker and taller as you get towards Inuvik. In this picture here, there's at least 10,000 thermokarst lakes. Most of them are quite small, only 1 to 100 hectares in area, and 1 to 5 meters deep. And they're ice-free from about mid-June until mid-October. And the rest of the time they're covered by ice that can be over 1 meter thick. So our motivations for studying hydrology in this region: one, there's a whole bunch of lakes in this region that are quite variable in their properties. And we expect climate change to impact these lakes in the future as air temp increases and increases evaporation. We also expect rainfall and maybe snowfall to increase in the Arctic, although it's not quite clear what will happen from what I read in this region. And we know that if combining more extreme rainfall and permafrost thaw, we can get more rapid lake drainage, where permafrost thaw allows the entirety of a lake to drain away. And these events are triggered by high lake levels, so we want to know when these high lake levels might occur and in which lakes these high lake levels may occur. On the other hand, if it ends up being drier for the lakes in the future, which lakes are going to be vulnerable to desiccation? We know the lakes in the Mackenzie Delta have the potential to dry up if they don't receive excess floodwaters. So are there lakes here which may be vulnerable to that in the future as well as it gets hotter? And when we look at changes in lake surface area over the last decades, the way lakes respond isn't uniform. Some lakes are shrinking, some lakes are increasing in surface area. And we suspect that might be related to lake hydrology. So we think that the lake and watershed hydrology impacts a lot of the ways that lakes are going to be responding to climate change in the future. And our objective here is to determine how meteorological conditions and also lake and watershed attributes control the variability of lake water balances in this region. So a bit of background on our methods, some of which you've just seen a bit of, using water isotopes. So we have our 2 water isotopes that we plot against each other. And we create a local meteoric water line, which we have snow on one end and rain on the other end, so we can decipher between these 2 sources of water. When we plot lakes on this chart, they tend to plot to the right-hand side because they've experienced evaporation. And the more they evaporate, the closer to this point, delta star, they get. And we can calculate this point using local air temperature and humidity data. So if we want to know the mixture of rainfall or snowfall in a lake, we can calculate that by kind of unevaporating the lake water in this direction. And we can see where that inflow or delta I composition falls along the local meteoric water line. So example, this lake would have a quite rainfall influenced source waters. And then we can deduce that the water that's in this lake was mostly sourced from rain. We can also calculate something called the evaporation to inflow ratio, or EI. And we just calculate that by seeing how close the lake isotope composition has gotten to this delta star point. And if, for example, we have an evaporation inflow ratio of 0.5, that would mean that 50% of the inflow to that lake has evaporated. So we know if that number gets above 1, the lake is eventually going to dry out if it sustains that evaporation inflow ratio. So the source water composition and evaporation inflow ratio are the two key hydrological parameters we focus on with water isotopes for this study. So we wanted to sample a wide range of lakes, and they very nicely built a highway for us a few years ago that spans across this environment, which gives us very easy access to a bunch of lakes in this region. So we sampled 25 lakes along the Inuvik-Tuktoyaktuk Highway 5 times in 2018, and we calculated evaporation inflow and the delta I for each sample. So here's our 5 sampling dates. 1st of May was the first one before snowmelt had occurred. Then we sampled after snowmelt and a few times during the summer. And we tried to sample kind of during dry periods and during wet periods so that we could evaluate how the water isotope composition changed in response to these different hydrological events and sort of meteorological conditions. We're also interested in watershed characteristics and how they influenced EI and delta I. And for this talk, I'll mainly focus on just watershed areas of lakes, and specifically the ratio of watershed area to lake area. So we take the area of the watershed and divide it by the area of the lake. And that ended up to be a quite useful predictor of lake hydrology, and we ended up calculating this ratio for all the lakes in the region to get an idea of the sort of regional variability we would expect in lake hydrology. So now, first I'll go through the results of the seasonal variability and how lake water balances changed over the course of our sampling period. So on the bottom graph here, I have the meteorological data, and on the right-hand side, we have the inflow composition, and here's snow and rain as a reference. Here we have the evaporation inflow ratio of all the lakes for each sample period. And this is just the change in the evaporation inflow ratio between the sampling dates for these 4 periods, which are different colors here. So the first period was when all the snowmelt occurred in this region. There's only, I think, 25 millimeters of precipitation. And we saw that the evaporation inflow ratio decreased because the lakes were ice covered for this period. And interestingly, the delta I did not become snowfall lake, and it stayed mostly the same. And we think that's because that there was snowmelt bypass occurring in these lakes. So the snowmelt water flowing into the lakes didn't mix very well with the water underneath the ice because of differences in density between the lake water and the inflow water. And a lot of the snowmelt runoff just flowed out of the lake without really replacing the pre-snowmelt lake water. And the second period was very warm. It was the warmest period, and it was very dry as well. You can see there's maybe only 30 millimeters of precipitation during this period. And lakes were ice-free for the whole time of this period. And as we expect, the evaporation inflow ratio increased, and the inflow composition didn't change very much, indicating that the lakes didn't receive much inflow, which isn't surprising because there wasn't very much precipitation. Now we go into a short period, the third period, where we had 45 millimeters of precipitation in a week, which is a good chunk of the yearly rainfall. And surprisingly, the evaporation inflow ratio of lakes didn't change very much, and the inflow composition of lakes didn't change very much either, despite all this rainfall that happened over a very rainy week. Then towards the last period, which went from August to early September, it was a much cooler and wetter period with lots of precipitation, like 65 millimeters. And now we started to see evaporation inflow ratios decreasing, and the inflow composition became much more rainfall-like during this period. So from these 4 periods we knew that the weather was quite typical for the most part in terms of the climate compared to the average climate year. And we characterized the lake water balance into these 4 phases of the year. So the freshet phase, we saw decreases in evaporation inflow ratio and a slight decrease in the isotope composition towards the average between rainfall and snowfall, but the lakes didn't necessarily get more, very close to the isotope composition of snowfall, indicating that a lot of the water was sourced maybe from the active layer as it was thawing and the snowmelt runoff was mixing with that active layer water, which was likely rainfall from the previous year. And the evaporation phase, we call it, where it tends to be not very much rainfall in the first half of the summer, and it's the warmest time of the year. We would expect that the evaporation inflow ratio typically goes up like this during the year. An interesting phase is maybe this transition from the warmer part of the year to the cooler and wetter part of the summer, where the soils are probably drier and they are not able to generate any runoff yet. And the lakes aren't responding to this initial transition to the cooler and wetter part of the summer. And we call that the soil wetting phase. And then the recharge phase, it's getting colder and rainier during the end of the summer. And we start to see more inflow and less evaporation, and the evaporation inflow ratio is decreasing and the inflow composition is becoming more rainfall-like. So in terms of seasonal variability from year to year, we had a quite rainy fall. There was a lot more rainfall than a normal year, and we expect that the isotope composition we sampled in early September might be more representative of a sampling date in late September if it was a kind of climate average year. But as we saw in the past graph, there's a lot of overlap between all these sampling dates, and we wanted to look to see how lakes varied in terms of their watershed characteristics. So in terms of evaporation inflow ratio, the ratio of watershed area to lake area was a very strong predictor of evaporation inflow ratio. There was an R-squared of 0.74. So as the relative size of a lake's watershed decreased, the ratio of evaporation to inflow is increasing. And it's increasing quite rapidly as you get to the left-hand side of this plot, which is a logarithmic x-axis. Yeah, so we had some outliers here, which are the triangles. Those were lakes that were fed by other lakes. And because those lakes are receiving evaporated waters from the upstream lakes, they get a bit of an erroneous estimation of evaporation inflow ratio. For delta I, it was honestly a bit disappointing. We saw this latitude effect where lakes closer to the ocean had a more rainfall-like inflow composition, but that's because the precipitation near the ocean is higher, because as the water vapor moves over the landmass, the isotope composition of the precipitation is changing. So we didn't see any snowmelt differences between the north and the south, even though there's differences in snowfall between the north and the south of this region. So as I mentioned earlier, we wanted to upscale this relationship between evaporation inflow ratio and the watershed area lake area ratio. So we mapped all of the watersheds in this region, which is about 7,500. And we looked at the distribution of this ratio through the region. Most of the lakes have a watershed area lake area ratio that's less than 5.5. And it looks like there might be a natural limit where below 1.5, we didn't find many lakes with this ratio that's smaller, suggesting that maybe there's a limit where a watershed isn't big enough to sustain a lake. And we wonder if this natural limit may shift in the future. When we apply this relationship between evaporation inflow ratio and watershed area and lake area to all our watersheds in our study region, we see that some lakes don't experience any evaporation at all, likely because the water is flowing in and out of the lake so quickly. So about 7% of lakes essentially are almost like an open river channel, and water is just flowing straight through them. And we think this could be useful for upscaling. So we had a really strong relationship between these two variables, and we think that it could be useful in predicting which lakes may be vulnerable to change in the future. So lakes with smaller watersheds maybe are more vulnerable to desiccation. Lakes with larger watersheds maybe are more vulnerable to changes in lake levels because they're receiving more inflow, and maybe they're more likely to experience rapid drainage.
Yeah, I think Evan will need to just grab our next speaker.
Okay, thank you.
Okay, our last speaker before the 10-minute break, and I do encourage, if you have any questions, throw them in the chat, and at the end of this speaker we'll have a 10-minute window to ask some questions. I do actually have a question for you, Evan, so if you're available. So our next speaker is Aaron, talking about plant water uptake is distinct, opportunistic, and controlled by seasonality and precipitation in a subarctic alpine environment. Take it away, Aaron.
Awesome. Thanks, Pete. Hi, everyone. My name's Erin, and I'll be presenting some of my PhD work on plant water uptake in a subarctic alpine catchment. This catchment is visualized here, and it's located on the traditional territories of the Tohono O'odham Council and Kwanlin Dun and Carcross-Tagish First Nations. So thank you to all the funding sources, and thank you to all the people who helped me dig many, many soil pits that contributed to this data. Some of them are shown here. So the north is rapidly greening. We're seeing these increasing, advances in tree line advance with increasing altitude and elevation. And we're also seeing increases in shrub height, extent, and densities. And so this is a term that's deemed shrubification. So this is happening all across high latitudes and has been confirmed for a number of decades now. We're also observing this shrubification in Wolf Creek, which is my research watershed, which is located just south of Yukon, which Lauren discussed earlier. And as you can see from the picture below, in the last 20 years, some of our instruments have been engulfed in shrubs. And this was confirmed from the air using 2 LiDAR flights in a recent publication by Sean Leapy and Sean Carey, looking at detectable changes in shrub cover over 10 years. And as you can see, it's quite substantial. So when we're thinking about what implications this has hydrologically, we have to remember that these landscapes inherently are heterogeneous to begin with. In subarctic alpine landscapes, we have boreal forest at lower elevations and shrub ecosystems at higher elevations, and it varies even across Wolf Creek here. And so if we're going to be predicting water yield across, watershed scale and, across these large swaths of the north, then we're going to have to be able to quantify what this means hydrologically. And not only are we changing the vegetation cover, we're also changing precipitation inputs as well as climate drivers and air temperatures. So some of the processes that this affects are total evaporative losses. We're going to be changing our transpiration dynamics, our T to ET, which is poorly understood in these environments. And then something I'm going to discuss more today is a bit more in terms of this ecohydrological partitioning. So as we change the timing and magnitude and phase of those precipitation inputs, and as this is exposed to different areas of the landscape, it's going to be stored differently, whether that's intercepted, held in soil water storage, and how that's partitioned in terms of blue and green water fluxes has a really large implication on downstream hydrology. And so for a number of decades now, stable water isotopes have been used as these tracers to track blue and green water fluxes. And most of the data has been focused in Mediterranean temperate climates. There's been recent attention drawn to northern environments, but this is still a very data sparse area in terms of understanding these blue and green dynamics. Typically in hydrology, we view these compartments in the landscape in the critical zone, and we assume that they're well mixed in our models, and that's not always the case. So understanding and quantifying the water fluxes, as well as identifying these plant water sources, will really help our understanding of rates of recharge and runoff, plant water use, residence times, and ages of water, and then the inherent and associated geochemical interactions. So some of the research questions I address in my thesis and in today's talk are shown here, and this is how I'm going to structure the results section of the talk. So I address how blue and green water fluxes vary temporally and spatially across these landscapes. I identify what controls and limits transpiration, which has a really large influence when we're trying to estimate what these ecosystems are going to do hydrologically as we increase atmospheric drivers. And then diving into the isotope world, how does soil and xylem isotopic composition vary among sites in between years? And what sources of water in the profile are these subarctic plants accessing, and at what times of year? So we've instrumented 3 sites in Wolf Creek. So we have a lower elevation white spruce boreal forest that's about 20 meters in canopy height. We have a mid-elevation buckbrush site, which has willow and birch shrubs that are about 1 to 3 meters. And then we have a sparse shrub site, which is very appropriately named. It's sparse willow and birch cover that's about 0.5 meter in height. And so these sites represent the space or time analogy, but they also represent these different thermal regimes. So again, the green here is the mean growing season length at each of these ecosystems, which has a really large influence on our green and blue water fluxes. And additionally, although it's not shown here, there are very different ground thermal regimes when we're altering the vegetation across this landscape, which also can affect all of these processes as well. So as part of my previous work, I've looked at these total evaporative losses across these ecosystems, and our forest evaporates more than our shrub sites, and it also receives less precipitation. And so what that means is that, at these figures in the top right here, our growing season water deficit at our shrub sites is, close to 0, even in a surplus depending on the rainfall in some years. Whereas our forest is always operating in this significant water deficit throughout the growing season. And this is indicating that these systems are more reliant on snow water, which I'll come back to later. We also measure transpiration, and I won't get into the nitty-gritty details of this. I'm happy to discuss if anyone wants to contact me after. But we installed Banyan-style sap-flow sensors at the forest and in white spruce, and then we also installed Dynamax exoskin sensors on birch and willow species at buckbrush. And then we upscaled it using plot scale measurements of sapwood area, and then did some gap filling to get some seasonal estimates and compared it to the ET from the eddy covariance instrumentation. So then we also did a lot of soil and vegetation isotope sampling. So we dug a lot of soil pits. Over the 2 years, we did 21 different sampling campaigns where we went to each site, dug 3 soil pits, and took 3 replicate samples from multiple depths, as you can see here. And then we also took cores to get xylem water samples from the white spruce, as well as stem samples from the birch and willow shrubs. And we sent them off for analysis, and then I've run a Bayesian mixing model to calculate some of the relative source water proportions of plant water uptake from different soil horizons, which will come later in the results. Sean always jokes that I should put a money sign beside this slide because there was a lot of data and time and energy that went into this data collection. So in terms of our interannual transpiration and ET dynamics, we had these 2 really distinct years in terms of climate. So 2019 was warmer and drier. July was about 2.5 degrees warmer than the long-term mean. And 2020 was substantially wetter and a little bit cooler than the long-term mean. And so what that meant is we could compare these 2 years and the responses between these ecosystems. So at what we saw in terms of our TDET, our buckbrush site, our shrub sites had really high transpiration rates in the middle of the growing season. So, our TDET was over 80% in the middle of the growing season. And this was suppressed in 2020 when it was cooler and wetter. And so we saw this large variability between the 2 years, whereas at the forest site, even though the climate was very different, we saw this about 50% TDET and similar transpiration rates. So this is highlighting some of the different sensitivities of these ecosystems, as well as the really strong influence of the seasonality at the buckbrush site. So we also did an analysis, boundary line analysis, where to evaluate the seasonal and interannual limits to transpiration. So essentially, we've identified these factors here as likely the most limiting to transpiration, and we've established these upper limits of stat flux density, which is on the Y here, and against these different meteorological variables. And so we wanted to establish, what factor is the most limiting to transpiration, and they're very similar to the drivers. And I know that this is a very colorful slide, but I did want to draw your attention to some aspects of this figure. Our moving mean stat flux density is shown here. Green is buckbrush and blue is forest. And so the main difference is what you're looking at here in terms of the colors are the colors represent the most limiting factor during that time period. So for example, if you just look at the forest sites for a moment, we can see that in 2019, we have a really large period where our volumetric water content is limiting transpiration, and we don't see that in 2020. So those different precipitation regimes really dictated what was limiting the amount of stat flux density. And at buckbrush, we saw that these systems, even in the drier year, we didn't see any soil moisture sensitivity. And so these systems were more energy limited. So again, when we had wetter season, T was suppressed at buckbrush and fairly consistent at the forest, but we did see this potential for moisture stress at the forest site. And now diving into the isotopes. So what you're looking at here is the dual isotope plots from both years for all 3 sites. And so we saw distinct differences between the forest and the shrub sites. And one of the interesting aspects is the white spruce xylem water was plotting a little bit farther down the line and closer to our snow water inputs, particularly early in the year. And so this again circles back to that the indication that those forests are more reliant on that snow water than our shrub sites. Additionally, we saw that the shallow soil depths of the forest showed evidence of increased soil evaporation relative to the shrub sites. So some interesting inter-site comparisons here. When we looked at this between years, again, we can see that 2019 was more variable, both in terms of its soil, water, soil and xylem isotopic composition. It was just simply more variable in 2019. And in 2020, if you ignore these 5 centimeter values, the soils were typically more mixed in 2020. And if you look at the bottom left here, we also saw some significant differences between years in terms of xylem water of all the species. And notably, our birch species plots lower and has a more negative LC excess, which can indicate increased evaporation. And so we were wondering if that was potentially evaporation through the stem, or perhaps these birch were sampling shallower soil depths, which were more evaporatively enriched. And so we used the mixing model to dive into this. And what we found was that even though the overall uptake of the shrub species were very similar, especially compared to the forest, which were a little bit more distinct, our shrub species were slightly different. So we did see a slightly higher uptake from shallow water at the birch than our willow. So this is just an indication that these species may matter and may be behaving slightly differently at these sites. And then finally, this is the mixing model result. So each bar represents different relative contributions from different soil layers to plant water uptake at the sites in different years. And we can see that this mixing analysis really reveals that it's variable between years. So in 2019, we had a slightly deeper sampling when it was drier. And then in 2020, when the soils were well mixed, we had this more variable response. And again, it's important to note the scales of these, this is volumetric water content, but the buckbrush site really never gets incredibly dry, whereas the forest site, we were reaching suctions that were below -1,000 kPa during that season. So very different moisture regimes, but these overall, these vegetation don't seem to be selectively uptaking water. They aren't pulling from tightly bound pore water. They're really just opportunistic, and so they're grabbing whatever available moisture is available to them at the time. And so this is just my last little interesting tidbit that I've kind of been exploring throughout my PhD is, do species matter? And so I'm not going to go through each one of these plots, but that banner at the top just sort of gives you a line of evidence of what I'm exploring in terms of, does it matter if, birch take over, willow take over? So my answer in terms of these multiple lines of evidence is yes, it does seem to matter. So our stat flux densities seem to be different between species. our drivers seem to be different between species. And then plant water uptake in terms of what maybe the rooting depth is different. And then I also took some stomatal resistance measurements with a barometer as well, and we found significant differences between the two. So overall, plant water uptake is distinct, opportunistic, and controlled by seasonality and precipitation. And we're going to see these variable responses across the landscape in responses to climate forcings. So thank you very much, and I'm happy to answer any questions now or after the session.
Great, thanks, Erin. Does anybody have any question for Erin or for Evan? I do actually have one for Evan, so we'll start with Erin and then we'll go from there. Oh, here we go in the chat. Jason, just 1 second, make it a little bit bigger. Great talk, Erin. Could you comment on the soil property changes, example, depth, porosity, associated with these shifts in vegetation across the north? Are changes being expected, observed, or is that something that may happen at much longer timescales?
Yeah, thank you for the question. I think the changes in soil properties will happen on much longer timescales. I know there's a lot of work being done in terms of, what's the limiting factor for tree line expansion. And I can't speak to it too much, I'm hydrology background and less of a biologist, but I think that the timescale is a little bit longer than the immediate change in vegetation. And then I think that we'll have longer term ramifications.
Okay, and I see a question from David.
Yeah, great. Great talk, Erin. Thank you. I was just wondering, have you considered doing any like labeled isotope wetting at a particular time during this at this site?
Yeah, I haven't particularly. I think it's really incredibly interesting. I would love to do it. I know that it's being done. I don't think it's being done on these species by anyone that I know, but it's definitely something to look into, and I think it's an interesting idea. There's no plans right now, but I think it's a great idea for the future.
Yeah, I have some colleagues that do some of this in tropical species, but like could be interesting to connect you, and maybe Sean.
Yeah, Sean's
Great.
next PhD project. Thanks for the question.
Okay, I will ask my question of too much money, Sean says, of Evan. But if people need a washroom break or something like that, then that's what this time is. I think we've got about 8 minutes left. So my question, Evan, so some of the systems I've worked in up in the James Bay lowlands, roads really impacted the sort of like gross flow across the landscape. And I was just curious if the roads impact or the highway impacts your lakes at all. I started kind of creeping on Google Earth and scrolling up and down the highway, and it doesn't look like you're getting wetlands formed along the side of the road. So maybe because it's permafrost, it's not a big deal. But do you have to go far enough away that like dust from the road would impact evaporative properties of the lakes or the vegetation around it? Or
Yeah, it's quite a new road, and I don't know so there's not much work about this road specifically, but they put in a lot of culverts so that there's not very many places where you get ponding on either side of the road.
yeah.
And I picked lakes where their watersheds, at least based on the digital elevation model, wasn't part of the road. But there is some dust depending on the year that kind of spreads out a few hundred meters either side of the road.
Yeah. And are your sites kind of like evenly distributed between east and west of the road, or are they typically all one side or the other?
I imagine it's quite random. I haven't really looked at that specifically.
Yeah, no, I was just curious. It's there was some students doing some amphibian work around Brandon, and she was looking at the impacts of the roads on the wetlands on amphibian habitat. But when you looked at the Google Earth imagery, it was pretty clear that those wetlands only existed because the road was put in, right? Like they were impoundment, if you will, wetlands. So like, I don't think that wetland would have existed before the road. So it was almost that the road was creating the habitat for the species as opposed to impacting it. So I was just I was get curious about roads.
Yeah, it's quite hilly there, so there isn't most of the places I've been there, it's not really very flat enough to get a peatland or anything like that.
Yeah,
It's all pretty well drained.
yeah, that's fair. Okay, so while we're kind of on this break, Pedro, Frank, and Rajesh, do you want to just quickly practice sharing your screen so we make sure we don't have any technical difficulties? If Pedro, if you're there, we'll start with you.
There is a question for Erin in the chat, Pete.
Oh, sorry. Thanks, Andrew.
And I'd like to ask one as well.
Do you have any thoughts on where alders fit into the range of ET from different shrub species?
That's a great question. I know that there was a recent publication from Katie Black looking at some sap flux work in alders. I think that it's, I'm not, sorry. Yeah, I'm not exactly sure. I think that there's just, these sap flux densities from these regions are typically fairly underreported. And in terms of, scouring the literature, I didn't see very many other, rates to reference, but yeah, alders, there's a little bit out there, but I'm not sure. I would assume that they behave similar to willows, but that's just sort of my first blush. Yes.
Yeah, we can see it. Pedro, do you want to just launch it to make sure it's not going to be in presenter mode, but we're getting the full screen?
Could I ask Erin a question?
Yeah, of course. I'm going to kind of do both back and forth between the questions and then getting the screen set up, if you don't mind, Andrew.
Sure. All right, so Erin, this very basic question because I probably missed it. You've got your flux towers measuring your total ET, I'm assuming, and you've got the sap flow from which you inferred the transpiration. And are you basically taking the differences of that as the blue water, as the evaporation, or did I miss something?
Yeah, so our total ET is our eddy flux, and then our we're just looking at those species that I've instrumented with the sap flow sensors as the contribution of transpiration. So there's a number of steps that have to go on before you can take the sap flux density and apply it at a plot scale, but essentially the transpiration that I was referring to in relation to the total ET was that one component, the contributing influence of that one of the species that we studied. Is that what you're asking?
Yeah, so basically the blue water, the evaporation, is the difference between those two. Is that right?
Oh, sorry, you mean just the direct evaporation? Yes, and so yes, essentially we're assuming that the difference between the two is the contributions from direct soil water evaporation and intercepted water.
Oh, okay, yeah, and interception as well, yeah.
Yeah.
Yeah, I always just kind of worry a bit about these methods. Not that you're doing anything bad, but you're doing something good. But the flux towers seem highly uncertain to me, and I think sap flow is also quite uncertain. If I'm not wrong about that, what do you think? Yes,
I mean I agree. There's a lot of inherent assumptions in this method. So I think that there's variability within the size and age of vegetation, and then just in the spatial area. So I think you have to be very careful when you look at, what footprint are you looking at with your flux tower, and then kind of is your data actually, or is your site actually homogeneous enough to be completing these, measurements. And so I think at the moment, there's a movement to have used like high frequency data from flux towers to partition out T to ET, but a lot of that hangs in the understanding of water use from plants. And so I think that there's maybe not a perfect way of doing it. I think this is the most direct way of doing it. And so in a lot of my work, I've tried to focus on, sap flux density as opposed to these ratios. I do discuss them, but I think you're right that it's flawed, but I think it's one of the most direct measures that we can have. And so it's a piece of the puzzle. And so that's why we're also trying to use the isotopes to try to back up the story as well.
Yeah. if you look in the textbooks, there's almost complete uncertainty about how much transpiration versus evaporation happens. I think, you know, the uncertainty band on that seems to be absolutely humongous. So it seems like a really good area that you're working in. And
It is,
remember during my comprehensive exam, I was asked, because I kept lumping them together, and the isotope specialist on my committee was getting very offended because they're completely different processes, and he didn't like my answer of, I don't care. It's just from a hydrologist point of view, it's just a loss of water from the system. So, okay, we will start up. It's 20 after, whichever hour you are in with. There you go.
Yeah.
I unmuted you, or I asked. You launch a presentation again?
Yeah. Okay. So okay. So I'll move to the next slide. So a little background about peatlands. Peatlands are a kind of wetlands made up of peat of more than 40 centimeters. And then we look at fens and bogs when we talk about peatlands. So why are peatlands important? They are important because of their ability to store carbon. And then they're also a source of horticultural peat. Now, overall, they're important because about 38% of Manitoba is made up of wetlands. And then of this wetland, 90% is peatlands. So that makes them important to study. Another aspect of peatlands is ecotones, which is the aspect that my research is focused on. So a little background. So ecotones mark abrupt transition between different ecosystems. So in peatlands, we have transition between fens and bogs, and then that is an ecotone. Now, ecotones are important because of their ability to exchange materials, water, and then nutrients between different ecosystems, and their ability to also detect changes in the ecosystem and then support biodiversity. So this is a typical bog with high water table. So what happens is that peat companies come and then create ditches in order to lower the water table and extract peat over a period of time. So this leaves the extracted peat unable to recuperate as it is exposed to high temperatures. And then there is an abrupt transition, as you can see here, created between the extracted peatland and then the surrounding peatland. Now, in the literature, one way of connecting the extracted peatland and then the surrounding peatland is to recontour and then to block the ditches that are created. So this is a typical peatland where we have a cutover peatland, we have a ditch, and then we have the forest. So blocking the ditch and then creating slopes, we can allow groundwater into the extracted peatland. And then during the restoration process, we can encourage an ecotone, and we can also help in the restoration process. Another thing is the creation of ponds and berms on the transitions in order to retain water on the slopes. Now, this has been used in cutover peatland restoration and has not really been used for transitions. And so my research seeks to also explore how these ponds and berms can influence the transitions. So the hypothesis is that creating ponds and berms on the periphery of extracted peatlands during restoration improves hydrological conditions. So the specific objective is to determine the impacts of the ponds and the berms on the water table and then water flow. And then we also want to see the best retention treatment that is needed to retain water on the slopes. So the research is in southeastern Manitoba, about 80 kilometers east of Winnipeg. We started the research in 2019 by instrumenting 8 transects with wells in order to measure water table. And then we also measured water elevation profiles along the transects that were instrumented. So with the results, here's the weather data. We recorded precipitations for 2019 and then 2020, which were the steady years. So both years had their total precipitations to be below normal precipitations. And then we also realized that the month of July for both years had the highest temperatures, with 2019 being below normal and then 2020 being higher than normal. And then the month of July for 2019 had the highest precipitation as compared to the month of June having the highest precipitation. But it is important to note that much of the precipitation was contributed to the month of July was as a result of a single precipitation event. So this is the elevation profiles that we did. So we have elevation on the horizontal, on the vertical, and then the distance along the transect. So this is, we have peaks and then clay, and then the minimum and then maximum water table showing here. Now, it is important to note that we applied recontouring in order to, as I said, reprofiling and then recontouring the slopes in order to help raise the water table. So we couldn't finish because of COVID, and also there was a very high precipitation event that occurred in the month of September. But then overall, we were able to recontour 3 transects. And then we compared the water table for 2019 and 2020. And then the transects that were not compared had similar elevation profiles. But if you look at the 3 transects that were reprofiled, you can see that the ones that were not reprofiled had their water table near the ditch to be declining, as compared to the ones that were reprofiled. We see a rise in the water table after reprofiling. Now, generally, water table increased by about 43 centimeters from 2019 to 2020. And then comparing the water table for the reprofiled site as compared to the site that was not reprofiled, you can see that water table was about 11 centimeters higher in the reprofiled on the reprofiled transect as compared to the non-reprofiled transect. So looking at the treatments that we applied on one of the slopes that we created, we had 3 treatments and then 1 control. So we have 5 pond and then 3 pond and then 2 berms, and then we have a control. So we installed wells across the treatments. So there were 3 experimental sections for the treatment. Now, in the result for the treatments, looking at the water table for the 5 pond was generally higher on the west experimental site. It was also higher at the south experimental site, but we did not see that at the northwest experimental site. But generally, the water table followed the same trend along for all treatments. We also regressed the water table for each of the treatments to the control. And then generally we can see that each of the treatments have a different slope, indicating that each of the treatments responded differently to water table, responded differently to the water table in terms of water table, the treatment, sorry. Now, generally we can see that the 5 pond, so what we should note is that the vertical here represents the water table treatment, and then the horizontal is the control. And then we have the unit line, which at any point that is above the unit line indicates a wetter zone, and then below is drier than the control. So 5 pond was generally wetter at all the sections, and then 3 pond was only wetter at the south section. But then, as we can see, the berms were wetter at all sections as well. We also installed tensiometers across the the treatments to measure the water tension. And then we realized that the 5 pond had the lowest tension. Now, lowest tension indicates that it may be the best treatment in terms of encouraging the establishment of sphagnum on it. So in summary, we can see that surface recontouring and then ditch infilling improves wetness, and then the location of a treatment applied influences its response. As we could see from the regression diagram that I showed, even though we had the same treatment at different sections, we could see that the same treatment had different slopes at the different sections. And then we also see that the 5 pond configuration maintained a relatively higher water table for all the sections. Then we can say that ponds and berms on artificial ecotone slopes generally play a significant role in regulating and maintaining wetness on constructed ecotone slopes. And understanding the groundwater characteristics on artificial ecotones can improve our understanding in achieving fen restoration goals. So I'd like to acknowledge the Canadian Sphagnum Peat Moss Association and their partners for funding through NSERC, and then my research committee, Dr. Riddington, Dr. McGonigal, and Dr. Struck, and then Alyssa Brewer, Vidley, Lyndon, Haley, and then Yona for their help at the field. Thank you. And I will welcome any questions.
Okay, thanks, Frank. We do have a couple minutes for questions. If anybody had questions for Pedro, he had to go, so you can contact him by email. So unless I see anybody raise their hand or just unmute themselves and start asking a question, I'll just remind people that we have the WU lecture tomorrow morning, which should be excellent. And then we have the CGUHS AGM tomorrow afternoon, evening, depending on where you are from. So if you're able to attend that, it would be great to get some of our members out to that. And then we have the CGU AGM next week on Wednesday, I think. Hopefully we'll be back in person in Banff next year. Very, very optimistic for that. And yeah, those are the main, I think the main things that are going on right now. Hopefully you're getting the who's who in the CGU HS. We'll have another one coming out, I think, at the end of the month. So if you know, we've kind of initially contacted 6 or 7 people. I'll be sending out an email to another 6 or 7 people. But if you'd like to be featured, or you think someone would be good to be featured, we are trying to stick more with faculty or government scientists. I know the COIS was thinking of doing something similar, highlighting student members of it. Oh, and that's the other thing, is that there's a CYS Young Hydrologists workshop shortly after this session, I think over the lunch hour, maybe it's a couple of hours long. So there's lots of hydrology related things to do over the next day and a half as we kind of wind down on the hydrology focused first half of the conference. Okay, our last speaker is Rajesh, talking about stream temperature variability and change across Western Canada. Rajesh, if you could start sharing your screen.
Okay. Can you hear me?
Yep.
Okay.
Perfect. Yeah, so you got 12 minutes. I'll turn my camera on, and then at about 15, I'll start interrupting.
Yeah. Thanks, Pete, for the introduction. And before I begin, I would like to acknowledge my co-authors, who are Jennifer Peskovich, also from Environment Climate Change Canada, and Sydney Hoffman, who is a student at University of Victoria. So water temperature is an important variable for ecosystem health of rivers, as many speakers have pointed out yesterday. And for example, elevated water temperature has been associated with high mortality rate of some of the aquatic cold water species. Water temperature also determines heat fluxes to the ocean and possibly affects stratification, circulation, and sea ice cover. And climate warming can be expected to lead to increase in water temperature. As we all know, Canada is warming at least 2 times the global average temperature increase. So that can be expected to have quite impact on water temperature regime in Canadian rivers. So before starting to look at how the water temperature will be affected or changed in future climate, the first thing we need to do is to establish a baseline condition and look at how water temperature has been changing in the historical climate. To that end, it's not changing. I don't know what's going on. Sorry, I'm stuck here.
Do you have multiple monitors?
Yeah, I have multiple monitors, but I'm stuck
Is
here.
your
I can't-
mouse not on the main PowerPoint, like on the background
It
slide?
is.
Sometimes. Oh,
It is. Yeah. I don't
can
know
you
what's
use your
going on
arrow
here.
keys left and right rather than mouse
No,
click?
I think I'm completely. My PC is hanging here. I can't do anything. Oh. Maybe- I'll stop sharing. Maybe that'll help. Again. Try again. So is that working?
Yep.
Okay. Sorry about that. So I don't know what was going on. So talking about looking at historical variable of water temperature regime, study led by a colleague of mine, Dai-Ching Gang, recently looked at the heat fluxes from rivers draining into Arctic Ocean and Hudson Bay. And we looked at 15 different rivers across Western Canada, and we found that water temperature data is highly variable across different river systems. And when we were doing the water temperature fluxes to the oceans, one thing that we realized is that it is highly uncertain because of the limited water temperature data. The figures here from Mackenzie River at Arctic Red and Fraser River at Hope exemplifies water temperature data available in different rivers. These two rivers we can say are relatively data-rich rivers in terms of water temperature data. For example, for Mackenzie River, we have quite a good density of data. Fraser Hope, we have also good density of data, and is actually better after 2005, where we have data that are measured or available daily or even sub-daily resolution. But if you want to do a historical baseline of water temperature data, we're still stuck with these samples that are collected once or twice a month, sometimes even less. And for some of the rivers, that is even less. So there are a lot of uncertainties using water temperature data like that for historical trend analysis and establishing baseline conditions. So one way to address that issue is to do a model-based reconstruction of water temperature for the historical climate. And for that purpose, we are using a two-model approach. First model we are using is this air-to-stream semi-empirical model. We are using that for reconstruction of historical water temperature. So far, we have reconstructed data set for 72 stations in Western Canada. We are using that data for evaluation of historical trends and evaluation of relative controls of different climate variables on water temperature. So the figures here shows the reconstructed water temperature data. That's the mean July-August water temperature. We see quite a bit of variation. I don't know if it's visible here. So the red is the higher temperature. The yellows colors are the lower temperature. So quite a bit of variation. So in the interior is higher temperature than in the coast. But we are not really convinced that this air-to-stream model is an appropriate tool for projection of future climate impacts. So for that reason, we are using a second model called RBM model, developed at University of Washington, because it is a process-based model and it represents different processes better in a better way. We feel that this is much more appropriate than using a simple air-to-stream semi-empirical model. That may lead to a question, why not use RBM for also reconstruction of historical water temperature data? We can, of course, do that, but RBM itself is a quite complex model. It requires a hydrologic model set up for a basin, which we don't have for many of the basins. So because of that reason, we are using air-to-stream model. And in this presentation, I will focus mainly on air-to-stream results. So as I said, air-to-stream is a semi-empirical model. It uses only two data sets, air temperature and discharge for the simulation of water temperature data. So the model is quite popular. It has been used in many, many locations because it's very simple to use and it seems to give reasonably good results in many areas of the world. And it's also gaining in popularity in Canada. I've seen application of this model in Fraser River, Mackenzie River, and other rivers as well. So going straight to the results here, we can see that the air-to-stream model is able to reproduce the variability of low and high water temperature reasonably well. The different goodness of fit matrices like Nash Cliff coefficient are close to 0.9 for most of the rivers. R squared is close to 0.9 as well. And the mean absolute error is less than 1.5 for most of the rivers. So after reconstructing this water temperature data sets, next thing we did was to look at the controls of discharge and air temperature and water temperature. We use this multiple linear regression approach and look at the controls. And what we found was a kind of distinct pattern between the north flowing rivers and south flowing rivers. For north flowing rivers, we saw that the temperature has much more dominant role than discharge. And for south flowing rivers, discharge and temperature are almost equal in most cases. So both of them seem to act on the water temperature data. This figure here also exemplifies the control of discharge and air temperature on water temperature. The north flowing rivers here are shown on top. So higher controls of air temperature as shown by the stratified pattern along this x-axis, which is air temperature here. So we see a higher water temperature for higher air temperature. For south flowing rivers, we see the influence of both discharge and air temperature. So we see not only that water temperature is higher for higher air temperature, but for lower discharge, we see higher water temperature as well. So both of these factors seems to play a more important role in south flowing rivers than in north flowing rivers. Looking at the trends, we see that trends in air temperature, discharge, and water temperature, we have compared for 17 stations here. So the stations with significant trends are shown by this filled symbols here. So for air temperature for July and August months, again, we see that for some of the south flowing rivers, we see significant increases in air temperature. Discharge, there are no significant increases or decreases. But in case of water temperature, we see significantly increasing water temperature for south flowing rivers. Air temperature here seems to play a more important role for this significant increase in discharge, increase in water temperature for the south flowing rivers. But beyond that, we see that also for south flowing rivers, discharge is decreasing at higher rate, although not significant compared to the north flowing rivers. So decrease in discharge may also be playing a role in increase in water temperature trends. We also considered or we looked at the sensitivity of water temperature in relation to air temperature and discharge. So what we did was we perturbed air temperature by 2 degrees and discharge by 20%. We decreased discharge by 20% and increased air temperature by 2 degrees. So what we found was kind of interesting. The effect of 20% discharge decline is about half of 2 degrees increase in air temperature. And the amount of decline in discharge, amount of decline in water temperature is actually lower than the air temperature decline. So it's lower than 2 degrees. That's what we found from the results. But we still feel that we need to look at other models to see if this result is reasonable or not. To summarize, so AirStream seems to provide an efficient tool for water temperature reconstruction. We see high spatial variabilities and sensitivity and trends of water temperature across Western Canada, which is not surprising. Next step will be to set up a river basin scale RBM. We are working with the developers of RBM to make it more usable for Canadian conditions. So that will be next thing to do. And then we'll be comparing air temperature results with RBM. And we would also like to share the results for anybody interested in open data platform, the results using the AirStream model. I will conclude by acknowledging the data providers, Water Survey of Canada, Freshwater Quality Monitoring and Surveillance Division of Environment Canada as well, and Alberta Environment. Thank you. I'll stop here.
Excellent. Thank you, Rajesh. I saw a comment from Jason. Why do you think the south flowing rivers show a stronger influence of discharge than the north flowing rivers?
There may be a number of reasons for that. So north flowing rivers, they don't really have low flows in summer. So compared to south flowing rivers, although there's no well-defined low flow in south flowing rivers as well. So small fluctuations in discharge in south flowing river probably will have a more important, bigger role than in north flowing rivers where discharges are relatively high, even in summer. That may be one reason. And other reason may be the ice cover and rivers and the snow melt driven flow coming to the river. So there are many factors. There may be many factors which may be affecting.
Okay, I think that is roughly our time for the session. So I'd just like to thank all of our speakers in all of the 4 general hydrology sessions. I think I chaired 3 of them and Barrett chaired the number 3 yesterday. So again, Young Hydrologist Workshop over the lunch hour, Woo lecture tomorrow, and the AGM tomorrow afternoon, evening, depending on where you are coming from. Thanks to all our speakers, and if anybody has any questions, I think you can use the platform to try to get in contact with speakers directly. Have a good morning, afternoon, or evening, depending on where you're from.